All right, let's talk about probability. And I know what you might be thinking: math, formulas, textbooks. But forget all that. Today, we're going to look at how we can find surprisingly predictable patterns in a world that seems, totally random.
So let's just start with a super simple question. If I flip a coin right now, can you predict whether it's going to be heads or tails? No, of course not, right? A single toss is a total mystery. And that, right there, is where our whole story really kicks off.
But watch what happens when we don't just flip it once. Look at this chart. After just a few tosses, the average number of heads is, well, it's all over the place. But as we keep going, past 50, then up to 100 tosses, you see that wild line start to calm down. It settles in, getting closer and closer to that perfect point 0.5 line. This is the magic we're talking about. Out of total chaos, a beautiful, predictable order emerges. So how in the world does that work? To really get to the bottom of this puzzle, we first need to get on the same page. We need a language, some basic building blocks to even talk about this stuff. First up is this idea of a random experiment. Now, that sounds way more complicated than it is. It's just anything you do where you don't know for sure what's going to happen. Rolling a die is a perfect example, sure, but so is checking tomorrow's stock price, or even just wondering if your bus is going to be on time. They're all random experiments. Okay, so for any experiment, you need what's called a sample space. I love this concept. Think of it as a complete map of every single thing that could possibly happen. So if we roll 2 dice, the sample space isn't just the sums, like 2 through 12, no, it's all 36 different combos, from a 1 and a 1 all the way up to a 6 and a 6. It's the whole universe of possibilities. And once we have that map, our sample space, we can talk about an event. An event is just us taking a big red marker and circling a part of that map. Out of all 36 possible rolls, maybe we only care about one thing, the sum being 10 or more. We're zooming in from everything that could happen to the few things we're actually interested in. Okay, so now we've got the basic lingo down: experiments, sample spaces, events. We can describe what randomness looks like. But how do we actually measure it? How do we put a number on it? Well, here's our most powerful tool, and it's surprisingly simple. As long as every outcome has the same chance of happening, like a fair coin or a standard die, calculating the probability is just simple division. You just count up the number of ways your event can happen, and you divide it by the total number of things in your sample space. That's it. It's that straightforward.
So let's test this simple idea with a puzzle that totally messes with our brains. It's called the birthday problem. The question is, how many people do you need to get in a room before there's a better than 50-50 chance that at least 2 of them share a birthday? Seriously, take a guess. What does your gut tell you? 100? Maybe more?
The answer is just 23. That's it. With only 23 people in a room, the odds are already in your favor that 2 of them share a birthday. I know, it feels completely wrong, doesn't it? But the math is solid. So why is that number so incredibly low? Well, the trick is to flip the problem on its head. Instead of calculating the odds of a match, let's look at the odds of no one sharing a birthday. And this chart shows you that probability just plummets. With 10 people, the chance of no match is pretty high. But by the time you hit 23 people, the chance of no match drops below 50%, which means the chance of a match has to be over 50%. The birthday problem is just a perfect example of how our intuition is, frankly, pretty bad at probability. But it's not the only one. Let's dig into another famous puzzle where logic and probability give us a clear answer, even when our gut feeling screams the opposite. Okay, imagine you're on a game show. There are 3 curtains. Behind one is a brand new car. Behind the other 2, nothing. You pick a curtain, then the host, and this is the important part, the host knows where the car is, opens one of the other curtains, showing you there's nothing there. Then he turns to you and asks, do you want to stick with your first choice, or do you want to switch? Most people think it's 50-50, but let's break it down. When you first picked your curtain, you had a 1 in 3 chance of being right. That means there was a 2 in 3 chance that the car was behind one of the other 2 doors. Now, when the host opens an empty door, he's giving you information. He's not changing that initial 2 in 3 probability. He's concentrating all of it onto the one remaining door you didn't pick. So here's the bottom line. You should always switch. By switching, you take your initial 1 in 3 long shot and turn it into a 2 in 3 favorable bet. It literally doubles your probability of winning. That's using probability to find the right strategy, instead of just going with your gut. Okay, so we've been talking about events like sharing a birthday or winning a car. But to really model the complexities of the real world, we have to go beyond just yes or no outcomes. We have to translate these real-world events into numbers we can actually work with. And that's exactly what a random variable does. This is a huge concept. Think of it as a translator. It takes the outcome of an experiment, which could be heads or tails or it rained today, and it assigns a specific number to it. It's the essential bridge that connects the messy real world to the clean world of data. Let's go back to our dice. The actual outcomes are pairs of numbers, right? Like rolling a 2 and a 6. Let's say our random variable is just the sum of the two dice. So look here. It takes the outcome 2, 6 and translates it to the number 8. But it also takes 3, 5 and translates it to 8, and 4, 4 and translates it to 8. You see? It can funnel many different real-world outcomes into the exact same numerical value. And this is where things get really powerful. Because once we have random variables, once we can turn randomness into numbers, we can start to build these incredible models that actually describe the hidden patterns of the world all around us. And these patterns, these distributions, really come in two main flavors. You've got discrete ones for things you can count, like 1 head, 2 heads, 3 heads. Then you've got continuous ones for things you measure that can take on any value in a range, like the exact amount of rainfall. And what's absolutely incredible is that certain shapes of randomness just keep showing up over and over again in totally different fields. We give them names like the binomial distribution or the Poisson distribution, but there's one pattern that is by far the most famous of them all, the normal distribution, what everybody knows as the bell curve. And this bell curve is everywhere. Seriously. It describes the distribution of human heights, tiny errors in a manufacturing process, test scores, you name it. There's a deep mathematical reason for this, called the central limit theorem, but the takeaway is that this shape is like a fundamental signature of randomness in our universe. But that brings us to one final, really thought-provoking twist. When a computer, like in a video game or a scientific model, needs a random number, where does it get it from? Well, as this quote points out, it's not really random at all. The sequence of numbers is generated by a perfectly predictable, totally deterministic algorithm. Which leaves us with a pretty deep question to think about. We use these fake, pseudo-random numbers to model the universe, and they work perfectly. So if we can create such convincing randomness with just a simple set of rules, what does that say about the real thing? Is anything out there in our universe truly and fundamentally random at all?